Alright guys, I want to look at another KSP problem. This one is from the 2006 exam, and we are looking at the lead and barium salts. So let's check this problem out. We have a saturated solution being prepared by adding excess lead 2 iodide to distilled water to form a 1 liter solution at 25 degrees Celsius. The concentration of the lead 2 ion in the saturated solution is found to be 1.3 times 10 to the negative third molar. The chemical equation for the dissolution, which remember dissolution just means the solubility or the dissolving process of lead 2 iodide in water, is shown below. So we have our reaction. Tells us to write the equilibrium expression. Hopefully we can do this in our sleep at this point in time. KSP, like all equilibriums, whether it's K, Ka, Kp, Kb, whatever, is just going to be our products over our reactants. Now our products are aqueous, our reactant is a solid, so we actually will not be including our reactant. So we just end up with the concentration of the Pb ion times the concentration of the iodine ion, and of course the iodine ion is squared due to the coefficient. So pretty easy, straightforward. Next thing it says to do is to calculate the molar concentration of the iodine in the solution. How do we do this? Two different ways, just kind of like on the last one. We can either use stoichiometry, where we use the ratio between lead and iodine, or we can use an ice table. It's kind of up to you. I'm going to work it out using an ice table. So we have PbI2 going into Pb plus 2 and 2 iodines. And if you think about your ice table, we have 0 of this and 0 of this to begin with. We have plus x plus 2x, and we end up with the lead iodine being 1.3 times 10 to the negative third. So we already know what x is, because remember you would have an x here if you didn't know what that number is, which means this is going to be 2 times 1.3 times 10 to the negative third. Or you could do it this way, or if you have 1.3 times 10 to the negative third, we'll just call it moles, even though it is molarity of the lead iodine, or the lead ion, sorry. For every 1 mole of lead, there is 2 moles of iodine. So either way you do it, you're multiplying by 2. And what we end up with is concentration of the iodine ion is going to be equal to 2.6 times 10 to the negative third molar. Okay, not too bad. Let's keep going down. It then says to calculate the KSP. Again, we should be able to do this fairly easily. This is just plugging in the numbers we just calculated into our KSP expression. So KSP is a concentration of lead, 1.3 times 10 to the negative third, times the concentration of iodine squared. Iodine's concentration we just calculated is 2.6 times 10 to the negative third squared. And what we're going to end up getting here is KSP is going to be equal to 8.8 times 10 to the negative 9th. So not too bad. It's basically all equilibrium, or the same type of equilibrium we've been doing all the way along. The only thing that's a little bit weird about these is we have a solid we have to deal with. Or, well, not deal with, but you get what I'm saying. Okay? Alright, let's keep going. We have a saturated solution prepared by adding the lead iodide, so the same thing we've been dealing with, to the distilled water to form a 2 liter solution at 25 degrees Celsius. It wants to know what the molar concentrations of lead and iodine are going to be in this solution and justify your answers. So there's kind of 2 ways you can go about thinking about this. First and foremost, you can do it through basic logic, or we can do it through an ice table. I'm going to do it with the ice table just to kind of prove a point here. We have lead iodide breaking down into our lead 2 iodine, or lead 2 ion. Sorry, I keep saying lead 2 iodine when I'm meaning to say lead ion. All right, lead 2 ion and our 2 iodine ions. So we now know our KSP for this reaction. I'm going to get rid of that. 0, 0, plus x, plus 2x. Okay, and we know KSP, which is 8.8 times 10 to the negative 9th, is going to be equal to x times 2x. Sorry, that's messy. Let's try that again. 2x squared. Okay, and we can solve this out. Where we get 2x squared is going to be 4x squared, and then times x is going to give us 4x cubed equals 8.8 times 10 to the negative 9th. So if we solve this out, we're going to divide by the 4, okay, which is going to give us 2.2 times 10 to the negative 9th equaling x cubed, and then we're going to take the cubed root, and what we get is x is going to be equal to 1.3 times 10 to the negative 3. What does that mean? That means our lead is going to be 1.3 times 10 to the negative 3, and our I is going to be 2x, which is going to be 2.6 times 10 to the negative 3. Do you notice anything here? Our concentrations are the exact same thing they were. Why? Why is that the case? Because we are creating a saturated solution, which means there's still solid left over. Okay, and remember the solid, how much solid is in there doesn't matter as long as there is some solid in there. Okay, so what that comes down to is at 25 degrees Celsius, our equilibrium constant is 8.8 times 10 to the negative 9th, which means at 25 degrees Celsius, these two values are always going to be the same as long as the only thing in solution is our lead 2 iodide. So you could answer it going through and doing the math, or you could basically just answer it through the logic that just because there's more water doesn't affect where equilibrium occurs. Our molarity is going to be the same because KSP is the same because temperature's the same. So our volumes, or not our volumes, I'm sorry, our molarities are going to be the same value as they were in the first place. They're not going to change just because we added or changed the volume to 2 liters versus 1 liter. So in other words, just so you can kind of get your brain wrapped around this, with KSP, our molarities are independent of the volume. As long as we're dealing with a saturated solution, what that means is, again, there's ions and solid left over that are at equilibrium. If there wasn't saturated and there was no solid, you wouldn't have equilibrium at that point in time. It'd have to get to equilibrium, which means we'd have to add more of these. So think of your Q value again if you want to. But kind of keep this in mind. KSP is independent of volume as long as temperature is staying constant. So these two values are always going to be what they're always going to be at equilibrium. Okay, so let's keep moving on. Okay, we then have solid NaI being added to the saturated solution of PbI2 at 25 degrees Celsius. Assuming that the volumes of the solution do not change or does not change, does the molar concentration of the lead in the solution increase, decrease, or remain the same? And before you answer this, be careful. Did we add something to the equilibrium? Yes, we added sodium iodide. So up here in part B, just because we added water or we have a larger volume of water, it doesn't change our concentrations because we're still dealing with just the lead 2 iodide, which is going to be at equilibrium according to our KSP. Go back down to C. C, we're adding a new species. Whoops, sorry guys. We're adding a new species. We are adding sodium iodide. Well, what do we know about sodium iodide? Sodium iodide is a fully soluble salt, which means it's going to produce sodium ions and iodine ions. And that's non-negotiable. That fully dissolves and is going to fully ionize. Well, let's look at our equilibrium that's going on here, which is going to be our lead 2 iodide breaking down into some lead ions and some iodine ions. Notice here that both of these reactions going on in the same solution are producing the same ion. Remember, this is our common ion effect. Okay, what does the common ion effect do? The common ion effect basically means because this solution is producing a similar ion or the same ion, it's going to result in this shift in the equilibrium here. So think about it this way. We are adding iodine, which means we are adding a product. According to Le Chatelier's, if we add a product, what happens? It shifts towards the reactants, which means what's going to happen to lead? Lead is going to decrease. So does the lead concentration increase, decrease, or stay the same? It's going to decrease. Justify your answer. Due to Le Chatelier's, sodium iodide is going to increase the amount of iodine in solution, which means we're increasing the amount of product in this equilibrium, causing a shift towards reactants and therefore a decrease in the lead ion. Okay, let's keep going. We now get to a new salt. The value of KSP for the salt barium chromate is 1.2 times 10 to the negative 10th. When a 500 milliliter sample of 8.2 times 10 to the negative 6 molar barium nitrate is added, or nitrate, sorry, is added to 500 milliliters of 8.2 times 10 to the negative 6 molar sodium chromate, no precipitation is observed. So let's see what we're supposed to do with this. 1. Assuming that the volumes are additive, calculate the molar concentrations of barium and chromate in the 1 liter solution. Okay, well, how are we going to do that? This is actually fairly straightforward. think about it this way. Both the barium nitrate and the sodium chromate are fully soluble, which means if we were to write those reactions, BaNO3, not at equilibrium, is going to break down completely into barium ions and nitrate ions. Okay, same with the sodium. Sodium chromate, oops, I'm about to write sodium carbonate, sorry. Sodium chromate is going to break down completely into sodium ions and chromate ions. Okay, which means if we know the moles of this guy, we know the moles of the barium because it's a 1-to-1 ratio. Okay, same with this. If we know the moles of this, we can find the moles of the chromate ion. So how do we do that? Moles per liter is our molarity, and we have our volume. So we have 500 milliliters of 8.2 times 10 to the negative 6 barium nitrate. How do we find the moles? We take our 8.2 times 10 to the negative 6 and multiply it by 0.5, and that should give us our moles of our barium. Okay, and what that's going to give us is 4.1 times 10 to the negative 6 moles. So let's go back over here. If that's the amount of moles of our barium nitrate, 4.1 times 10 to the negative 6, that's also going to be the same amount of moles that we get for our barium ion, again, because it's a 1-to-1 mole ratio. For every 1 barium nitrate, we're producing 1 barium ion, and because this is fully soluble, we can make that assumption. So we now know the moles of the barium ion. We can do the same thing with the sodium chromate. Okay, same idea, and it's actually the same math if you look at it. It's the same molarity and same volume, which means it's the same amount of moles for here and the same amount of moles for the chromate. Again, same idea with the fact that they are fully soluble and it's a 1-to-1 mole ratio. Of course, our nitrate and our sodium would be twice as much, so if they were asking for nitrate or sodium, this would be 8.2 times 10 to the negative 6. We just don't care about it. We're looking at just the barium and chromate. Now, we're still not done. We now have to get this into molarity. Nice thing is, we're now in 100 liters. So divide by 1 liter, and what we get is our concentration for both the barium ion and the chromate ion. They're equal. Whoops, there we go. And that's going to be equal to 4.1 times 10 to the negative 6 molar. So let's keep going down and see what number 2 is going to ask us to do. Okay. Number 2 tells us the molar concentration of barium ions and chromate ions are determined above to show why a precipitation does not form. You must include in your calculation as part of your answer. So basically, using this number, let's figure out why no precipitation forms. Okay, this is kind of one of those things that we did in the last chapter. You're given 2 starting values and you're comparing it to K. We know K is supposed to be, if we go back up here, 1.2 times 10 to the negative 10th. Let's see where we are. Let's see what our Q value is. Well, Q is going to be equal to 4.1 times 10 to the negative 6 times, and let's go back up here and make sure we see what this is, 1-to-1 ratio, so our reaction would be going into 1 barium plus 1 chromate. Both of those are 2 technically. Okay, so 1-to-1 ratio, so 4.1 times 10 to the negative 6 to the 1, and 4.1 times 10 to the negative 6 to the 1. Okay, and what we end up getting is Q is equal to 1.7 times 10 to the negative 11th. Well, what do you notice about Q versus K? Well, K is greater than Q, which remember, if you write this in the order, we can determine which direction it's going to shift. That means it's going to shift towards the products, which means it's going to shift towards the ions. Think again to the reaction we just wrote up at the top up there. When this dissociates, we get the ions as the product. So it's going to shift towards the products, forming the ions, not actually forming the solids. We actually won't get any solid formation until Q is equal to K or until Q is greater than K. But because Q is less than K, think about it, products over reactants, in this case just products, it means our products are too small, it's going to shift towards products. Okay, so that's the 2006 exam. Again, this is some of the stuff you could expect to see in a KSP problem. Thanks, guys.